Hello guys, so this is the second of two videos that I made about repairing and modifying an old MIG welding machine. And while we focused on the welding machine's power or current source in the first video, this time we're going to take a closer look at the wire feeder and the electronics that control the wire feeder and other things inside the machine. So let's then just start to get the wire feeder running again, and as usual I first clean the out and the inside of the enclosure a little bit, also in order to familiarize myself a little bit with the details here. One neat thing, for example, we have this little door here that can be used to access the very spot where the welding wire leaves the enclosure and enters a, central connector. That's how we call it in German, Zentralanschluss. But right now you're actually not looking at the front side of that connector, but at a broken off plug that belongs to the hose package. And you might find that to be a weird word because it's a direct translation from the German Schlauchpaket. But, I think hose package might sound weird, but it really describes what we're having here. It's not just a hose, it's not just a wire or a cable. You'll see in just a minute. And this little threaded tube here, that leads to a little metal spiral called the liner, and that is where the welding wire is pushed through and guarded until it reaches, the tip or the nozzle of the welding gun. And the broken off copper tube here, that actually leads to the hose inside the hose package, which, transports the welding gas to the welding gun. But as you can see, it's broken off. And then, of course, there's also an electric conductor in here, which transports the welding current from the positive output side of the power supply to the nozzle of the welding gun. Now we could fix this thing here by soldering or brazing that broken off copper tube back in place, but that doesn't make too much sense because this old-fashioned connector here, this jack that is sitting inside the enclosure, is totally outdated, not according to today's European standards, so we couldn't connect a modern welding gun to this. So I will just replace this here with a new European type standardized central connector. But in order to replace the connector, I also have to take out the entire motor assembly. So I just remove a bunch of bolts and now I can lift it out of the enclosure. And after having unscrewed that really heavy welding cable in the back side of the enclosure, I can now also take out that entire central connector. But as you can see here, there's also some really old grease inside the enclosure, and that has leaked out of the reduction gearbox on the motor. And that can mean two things: that the grease has gotten too thin and or that the gasket is damaged, and we'll have to take care of both of those things. But first of all, let's test if the motor even runs, because that's the most important thing here. So what type of motor is this? It's once again a DC motor, but again not a permanent magnet DC motor, but a separately excited DC motor. In German, fremderregte Gleichstrommaschine. And I explained how this type of motor works in my video Inside a Washing Machine Motor just a couple of weeks back, and you can find that in the video description. In short, it simply means you have a DC motor and you control it like a DC motor. But unlike what you know as a permanent magnet DC motor, you don't have permanent magnets, but electromagnets creating an external magnetic field inside which the rotor rotates. So what you can do then is to supply a constant voltage, or rather current, to the field coils, those external electromagnets, and then you can vary the voltage across the commutator, or leading to the rotor, to adjust the speed at which the motor and thus the wire feeder is running. And we'll talk about that in more detail in a couple of minutes when we come to the actual motor control electronics. For now, I've just hooked this motor up to my variable isolation transformer and added a crude rectifier arrangement here. And as you can see, the motor is running just fine, but we should fix the issues with the gearbox before we go on. So I have now opened that enclosure which holds the reduction gear, and we can see a dark brownish, very thin grease that in my opinion has no real substance to it anymore. We should replace it. And you can also see, the remnants of the old gasket that, is kind of in shreds and as if glued to the metal. So what I did next is to take the entire reduction gear apart, clean out all the old grease, and I did that with a rag and gasoline. and then carefully removed all the remaining parts of the old gasket. And well, after that I took a piece of gasket paper and I kind of made a mask and used a knife to cut out a new gasket. So I inserted new grease inside the gearbox, of course after having put like the reduction gear back together. And then I put the box back together with the new gasket installed. And in the next shot you can see me comparing the old central type connector to the new standardized European central connector. It's just a conversion kit that you can buy for just a couple of bucks on eBay. I've shown that earlier in the video. And well, it's just a matter of really fitting everything together so that the wire is picked up properly just like before. So at least in my case here, it was really easy to fit the conversion kit to my old wire feeder assembly. And we're now in 2017 and in the new place, and as you can see, I've just bought a new welding gun and I'm connecting that to the new Euro central connector here. So, and I've now connected the motor to my lab power supply to test if the wire feeder is working. So let's try to pick up the wire and push that all the way through the liner until it comes out of the nozzle of the welding gun. Okay, so with the power source and the wire feeder running, we can finally start welding, right? Well, it's actually not that simple. The reason for that is that you want your wire feeder to be active and your gas valve to open, and optionally also your power supply to be powered up only when you push that little button on your welding gun. And in order to make that possible, you need an electronic circuit that combines all these things together. Also, you want the wire feeder to stop immediately after you have let loose of that button, so you need some kind of a brake function. And in order to make all that possible, actually there was still a lot of work ahead of me. I tried to repair the control electronics, but then decided to build some of them myself. And that took me a lot of work and a long time until I could actually weld. But through the magic of Hollywood, I can just take you through the practical side of these things very quickly, and then let's weld a little bit, and after that I will then explain to you how these electronics work. So the first electronic problem that I had to solve was to add a 12-volt DC rail to this machine so that I could power the fan that I'd installed last time. In order to do that, I first added a small transformer to the enclosure and then built a buck converter that would give me 12 volts DC for the fan. In the next step, I built another buck converter, similar but specialized to the task of controlling the motor speed of the wire feeder. In the next step, I also built a motor brake and added a little current sensor that we could use to measure the actual welding current for later projects. In the next step, all of these electronics had to be safely installed behind the front panel. I also had to install large relays so that I could switch on and off the power supply. In a final step, I also made some modifications to the wire feeder. For example, I added a 13mm welding jack to its front side so that I could use a welding cable to connect the plus pole of the power supply to the wire feeder, but still leave the option open to disconnect the wire feeder from the power source and use it for stick welding again if needed. And then in a final step, the two devices were connected together in various ways. So you've probably seen better welds in your life, sure, but well, I just built this circuit here myself and I just have to find out which speed setting for my motor controller is the best one for which welding current, and I'll probably need a couple of months to get this all just right, but for me, for now, this is a huge success. And I've spent a lot of time with all of the subsystems of this welding machine and I have learned a lot. So let me just talk a little bit about the details of how the old electronics worked and how the new electronics work that I've been talking about throughout the last 2 episodes. Okay, so we already talked about the circuit diagram of the power supply in part 1, and now we're going to talk about the circuit diagram of the rest of the electronics in the machine, and all this stuff and the stuff from last time are working together, of course, but it's impossible for me to fit everything on just one 1080p screen. So just keep in mind that the electronics from last time work in conjunction with the electronics that we're going to take a look at now. And we start again with our 3 phases and the neutral conductor, and we have another mains transformer, but this time it's a single phase transformer. It's the one down here in the bottom or here on the workbench on the left hand side, and as you can see it also has a variety of connections. On the primary side we find 5 connections and 3 tabs, and they have little labels as you can see, and I'll explain that in just a minute. On the secondary side we have several secondary windings. This secondary winding here has 5 connections altogether with the labels 32, 24, 0, 24 and 32. Then we have another secondary here, and then down here we have a third secondary that is internally also connected to the 0 tab. And all these numbers here that are conveniently labeled on the transformer are the RMS, root mean square voltage values, in German Effektivwerte, of the individual windings and tabs. And the voltage values on the primary side, 380 and 220 volts, tell us that this transformer can either be connected between one phase and the neutral or between 2 phases. Last time I told you though that the nominal voltage between 2 phases is 400 volts and between a phase and neutral 230 volts. So why do we have 380 and 220 on here? Well, the reason for that is that before 1987 the nominal line voltage in Germany was lower than today. And that happened as part of an international effort to harmonize the standards regulating the line voltages in different countries. And as you can see on the primary side, we already had back in 67 2 more tabs here saying plus and minus 10. And those are here to correct for a line voltage that is a little higher or a little lower than 220 volts. So since we might have, not necessarily, but possibly a higher line voltage here in my shop today, we'd better choose the tab that gives us a little more leeway. And you can see that I now connected the transformer between 2 phases and not to the neutral at all. And that's also how it was done originally in this machine. And the reason for that is that, well, they were building this machine so that it could be powered from the 3 phases alone, without any connection to the neutral conductor. And that's why they, well, used a single phase transformer that can also work without a neutral. But we also saw this switchboard here down in the machine, and the reason for that switchboard was that you could change a couple of connections so that this entire machine could also run on a single phase supply. Now in that case it couldn't deliver the same amount of output power, but it would be more versatile. Well, however, I will probably never do that because I have 3-phase power. So in order to make room inside the enclosure, I removed that switchboard. And because they built this machine so that it could run on single phase at 220 volts or on 380 volts 3-phase power without even a neutral conductor available, they had to put a 220 volt winding on the secondary side of the transformer. Because here is where our fan, that is powered by an induction motor with motor capacitor, would be installed. But the old fan broke, so I replaced it with a server fan. And that server fan needed to be powered with 12 volts DC, so I added a 12 volt power supply to this machine. There would have been easier ways, by the way, but what I did is to add another old mains transformer to this enclosure. That's the one on the right here on the workbench. And this time I had to connect it to the neutral because the primary of this transformer is only built for 220 or 230 volts. And then I rectified the output voltage just with a full bridge rectifier and charged that to an electrolytic capacitor. Up to this point, really the classic topology for a conventional power supply. But then I decided to build my own buck converter to regulate the output voltage. But I actually built a second buck converter, and I'll talk about the details here a little more in a couple of minutes. At this point though, I decided to also add a bunch of linear regulators to the circuit that will supply a plus 5 volt and a plus 15 volt rail. And these two voltages were needed for various control electronics. But I also needed plus and minus 15 volts, especially for this contactless current sensor that I'm testing here with a DC motor. Another one of the original circuits was the one that controlled the gas valve. And the gas valve is opened when a little electromagnet inside it is energized. And how they did that originally here is to first use a single diode to do what is called half-wave rectification, in this case to obtain a positive unfiltered output voltage. When you would then push the button on the welding gun, the circuit of that relay is closed so that it is energized, which would then energize the electromagnet inside the gas valve, and the gas would then flow. Now, I later found out that this gas valve works with both 12 or 24 volts and both with DC and AC, and I later deleted this old circuit here and built one with a MOSFET. The reason, by the way, why the chassis grounds in this circuit diagram are labeled with a little 2 is because I wanted to differentiate them from the chassis ground that I used in the first video. The two are not connected together. And in this case, well, even if the relay would close, the valve would actually not be energized because this chassis ground 2 is not yet really connected to this secondary winding here on the upper transformer. But we will resolve this in just a minute, you'll see. But I actually also needed a negative supply rail, minus 15 volts, for my current sensor, and I used this secondary winding here to obtain that. How did I do that? Well, I added another diode and again used half-wave rectification, but see, if you turn the diode around, then you will just get the negative half-wave. So you can charge that to a capacitor, and now you have to connect the plus pole of that capacitor to chassis ground. And if you want to regulate that voltage, you can then use a negative voltage linear regulator like the 7915 to obtain minus 15 volts DC. But what I just explained to you only works under one condition, and that is that we connect this tab marked 0 here, the center tab of the secondary, to the chassis ground as well. And now I can also show you how the motor controller for the wire feeder used to work. Now, I told you before that this is a separately excited DC motor, meaning that we have a field winding or field coil that has to be energized for the motor to run. And originally it was connected to this secondary, to the two 24 volt tabs like this via two diodes. And this is a rectification technique that is called full wave rectification with center tab. And the idea here really is that you can do full wave rectification with just 2 rectifiers instead of 4, as in a full bridge rectifier. Now, today that wouldn't make a big difference in terms of cost because diodes are very cheap now, but back in 1967 they were not. Okay, so maybe it helps to take a look at the actual waveforms here. If we were to plot the voltage V1 that's between the two 24 volt tabs, we would get something like this. It's a symmetrical and supposed to be sinusoidal alternating voltage, and it alternates between two peak values. The positive peak value, V1 peak, and the negative one minus V1 peak. And the absolute value for that would be 2 times 24, because we have two 24 windings, basically in series. And then we would multiply that times the square root of 2, and we would get 68 volts. Now, if you have a truly sinusoidal alternating voltage, then you can derive the peak voltages by just multiplying the RMS value by the square root of 2. It doesn't work, however, if it's not sinusoidal. Okay, so that would be the voltage that we would work with if we would just apply a full bridge rectifier to the two 24 volt taps, okay? But since we only use half of the secondary, our voltage V2, for example, between one of the 24 volt taps and 0 would be only half that. That's the gray line here. And then it's rectified, so VF, the rectified voltage at the output of that rectifier, would look like this. And well, the peak voltage here would be 34 volts, because that's 24 volts, the RMS value, times the square root of 2. But for many practical purposes, like driving the wire feeder, we can pretty much just neglect the fact that the voltage actually fluctuates between 0 and 34 volts, and we can just pretend as if we are applying a constant 24 volts DC to the field coils. Okay, so much about the field coils. But what about the voltage that is actually applied across the motor brushes, leading to the commutator and thus to the rotor that actually rotates inside the DC motor? And how is its speed adjusted? Well, here is the original motor controller, and you can see this black heatsink here. And attached to that are three components. One of it is a diode, but two of these are SCRs. Silicon controlled rectifiers, or thyristors, in German called Thyristoren, and well, they can be actively activated, after which they just act like diodes until the current through them drops under a threshold value, which happens every half cycle. So let's picture that here again with a little plot. We again connect the SCRs very similarly as how we connected the diodes before, but this time two little control pins, so to speak, are connected to a control circuit. And that fires these SCRs, it actively activates them within each half cycle, and we can then vary the time, the point in time within each half cycle where we actually fire the SCR so that it conducts, or they conduct, for a smaller or larger portion of that half cycle. And that then, well, leads to a lower or higher mean voltage across the commutator, and that leads to higher or lower motor speed. And that is how the original motor controller from the 1960s worked. This is a type of phase-fired controller, in German called Phasenanschnittssteuerung, which means as much as phase-cut controller. But the old motor controller unfortunately did not work anymore, and I didn't want to spend too much time to find out what was wrong. So I decided to just build my own controller then. That might sound like more work at first, but the thing is that in that case I spent a lot of time as well, but at least with modern technology. And while I'm by no means saying that it's a waste of time to learn about phase-fired controllers, it might pay off more now and in the future to learn about modern switching controllers. So let me show you then how I changed this entire design here. First of all, I replaced the SCRs with ordinary diodes, and let me make some room here for new components, to then connect an electrolytic capacitor to the output of that rectifier, and the voltage across that capacitor, at least in open circuit conditions, would be very close to the peak voltage. That's 32 volts times the square root of 2. And now you could just, for example, connect an N-channel MOSFET between one of the pins of the motor and the chassis ground and use a pulse width modulated square wave signal to switch that MOSFET on and off. And the plot of the voltage across that motor would then look like a series of rectangular pulses. And the idea here is again that you can change the duty cycle of that signal and thus also the mean voltage across the motor. So in a way the idea here is similar to what was done in the phase-fired controller, but in this case you're no longer bound to the line frequency, so the pulses that you typically work with here are much shorter, often in the kilohertz range. But this is actually not how I solved this. I didn't just use a simple N-channel MOSFET as a chopper, colloquially speaking, but I actually built a buck converter, and that means while I was still using a MOSFET to rapidly switch on and off that supply voltage, I smoothed out the output voltage so that the pulses actually don't reach the motor. The voltage across the motor is still adjustable though, because you can adjust the duty cycle of the PWM used in the buck converter. So this wouldn't have been strictly necessary, but I had already come up with a generalized solution for building switching converters, and the controller that I'm using works best with smooth output voltages. And that is why I just customized an already developed solution. But I also mentioned that you want to stop the motor really in its tracks once you let loose of that welding button. And that's why you need some kind of brake. And how I solved that is to add another MOSFET that simply very quickly disconnects the motor from the buck converter once you let loose of that button. And then I added another MOSFET and a very low resistance power resistor, and these components will just short circuit the motor in that same instance. So at least in the low to mid speed ranges, the motor really stops in its tracks once I stop pushing that button. In the really high speed ranges, it doesn't work perfectly yet, but as you have seen, it was good enough for welding at a high welding current anyway. So if I really were to go in the details here, I could go on and on and on with it, but I will just wrap it up here because I think that I have covered enough in this video. But we will revisit this machine and take a look at other welding machines in the future. For example, I have now bought one of these really cheap welders here again. And in order to give you something that you can maybe do at home, I will try to upgrade a really cheap machine like this in a future episode. But the next thing that I actually want to do, and I'm speaking about the next episode, well, that will probably be getting that lathe running. As you can see, I'm trying to catch up with these older things that I never finished. So no matter what will exactly happen, it'll be in the not too distant future, and it will be interesting, I promise you that.